it's important to understand what the angular acceleration of an object tells you in terms of an object's linear acceleration. If we have an object moving in a circular path, we already know that we have an acceleration on the object, and that's a centripetal acceleration. And we know that at any point that centripetal acceleration is going to be inwards towards the center of the circle. We know from what we were looking at in the past unit that the v squared divided by r is going to give us our centripetal acceleration. What I want you to understand is that there's two terms. This is not only centripetal acceleration, this will also be called radial acceleration. And it's a term that's more commonly used in our rotation unit. So centripetal acceleration and radial acceleration are essentially the same thing. When we're looking at our angular acceleration does not relate to our radial acceleration. Our angular acceleration relates more to what we call our tangential acceleration. So I'm going to call that a sub t. So a sub t is our tangential acceleration. And the reason why this occurs and why this is not our radial acceleration, if an object is moving at a constant, or I should say uniform circular motion, so if an object is moving at a constant speed throughout a circular path, there is no angular acceleration. And that's because the rate of the object's the rate of change of the object's angular velocity will remain zero. There is no change in the object's angular velocity, so there will be no angular acceleration. However, there still is an acceleration on the object that is due to that centripetal acceleration because it is moving in a circular path. So, in order to find the tangential acceleration, that has to occur when you have an object that is changing its angular velocity. We know that the alpha, the angular acceleration, is equal to the change in omega divided by the change in time. If we try to relate this to our linear acceleration, we know that the acceleration is equal to change in velocity divided by change in time. Well, what this means is that if I take my change in velocity, if I think back to my linear velocity, I know my linear velocity is equal to my angular velocity times the radius. I can say that this is delta omega times r divided by delta t. So what happens in this case, if I just look at delta omega divided by delta t, that's going to be my angular acceleration. So my linear acceleration can equal my angular acceleration times r. It's a very similar relationship with the linear acceleration and the angular acceleration, just multiply times the radius. It's the same relationship that you have with your linear velocity and your angular velocity. This is going to be my tangential acceleration. So that's what's important to understand here, is that tangential acceleration is equal to the angular acceleration times r. In terms of my radial acceleration, I can do something very similar here, where if I know that I'll use r instead of c. If I know that my v squared divided by r is my centripetal, my radial acceleration, if I just replace v with omega r squared and then divided that by r, I can have a relationship here where it's going to be omega squared r squared divided by r, which means my radial acceleration is going to be omega squared times r. That's a little bit different. That's not the same as the tangential acceleration. So it's important to understand the directions of each one of these accelerations. The radial is my inward, my centripetal acceleration, while my tangential is going to be my tangent. So the radial is always existing. Whenever you have an object moving in a circular path, the tangential acceleration only exists when you have an object that is changing its speed.